Hello. In this section, we are going to continue talking about how to do a hypothesis test for a population mean. But this time we will look at how do we do this if sigma is unknown. Again, sigma is the population standard deviation. And we discussed this back in when we were talking about confidence intervals, but because sigma is a number that is based off of an entire population, and we don't typically have access to the entire population, usually sigma is not known. And so if it's not known, we have to tweak our method a little bit to account for that. So what we're going to do is look at how to test a hypothesis about a mean using the p-value method again, which we introduced in the previous section. But this time we will look at how to do that when sigma is not known. And we'll look at how to do this both using a table and then also using your TI-84 calculator. So we'll begin with an example. Let's suppose that in a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was x bar equals 2.2 kilograms with a sample standard deviation of S equals 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? So, if you recall in the previous section, when we were working out a hypothesis test, we had to start by establishing our hypotheses, and then we had to compute the test statistic. And in that section, the test statistic was a z-score, which we found using this formula right here. Okay? In this example, though, what we see is that the standard deviation which is given is a sample standard deviation. So in the formula, sigma has to get replaced with S for the sample standard deviation. But as we learned back in Chapter 8 when we covered confidence intervals, when you replace sigma with S in this formula, the resulting variable is no longer a normally distributed variable. It's one that follows the student's t-distribution. So this is the formula for the t-value, and our test statistic in this case is a t-value instead of a z-score. Okay? And again, when what we do is we assume that the null hypothesis is true when we compute this t-value, and we say that it follows a student's t-distribution with n minus 1 degrees of freedom. Okay? So assumptions that have to be made here for performing this hypothesis test, we have to have a sample that is a simple random sample, and a sample size that is large or the population is approximately normal. The same assumptions that have to be followed for the sampling distribution to follow a normal distribution. So if we go back to our example, the weight loss example, right? In that example, we are told that we have a simple random sample. The sample size was 76, so that's definitely greater than 30. So our assumptions are satisfied, so we can proceed. The question was, or the issue that was being presented is whether the mean weight loss is greater than 0. So when we establish our hypotheses, the null hypothesis will be the assumption that nothing has changed. And if nothing has changed, then the mean weight loss would be equal to 0, nothing, right? And because the word greater is used, then the alternate hypothesis is being set up as a right tail test, mu greater than 0, right? So as for any test, we always start by establishing the two hypotheses. The next step will be to find the test statistic, but this time the test statistic will be a t-value instead of a z-score. So we'll plug in 2.2 for the sample mean, that's a given value. We are assuming the null hypothesis is true, so we'll plug in 0 for mu for the population mean. And Sample standard deviation S is given as 6.1, sample size N is 76. So when we work that out, we get 3.144. So we say that when the null hypothesis is true, the test statistic T follows a student's T distribution with 75 degrees of freedom, because 75 is one less than the sample size. This is a right-tailed test, which means that the p-value, right, the next step is to find the p-value, will be the area under the student's t curve to the right of 3.144, right? So that's the other difference here, is that the p-value, again, is the area under the curve, in this case to the right of the test statistic. But the curve is not a normal distribution curve. It's a student's t distribution curve. Okay. Now we're going to go over two ways to identify that p-value. And it turns out the only way to find the exact p-value is to use technology such as your TI-84 calculator. We do have a student's t-distribution chart, which we used in the section on confidence intervals. And we can also use that chart, but as we will see in a moment, the chart is not detailed enough to give us an exact p-value in most cases. It's only detailed enough to narrow down the p-value to within a range, which most of the time that's still good enough to be able to make a decision, because again, remember, we only have to be able to compare our p-value to our value of alpha, right, to make a decision. So in this case, if you use technology, you'd get a p-value of 0.0012. And that is clearly less than my value of alpha, which was given as 0.05. So we will reject the null hypothesis at the 0.05 level. Okay? And we conclude that the mean weight loss of people who adhered to this diet for 12 months is indeed greater than 0. So as you can see, the basic structure of how the test is conducted is the same, right? The only difference is the test statistic is now a t-value, and the p-value is an area under a t-distribution curve, not a normal curve. So let's talk a bit more about the p-values, right? The p-value of the test statistic is the probability, assuming that the null hypothesis is true, of observing a value for the test statistic that disagrees as strongly or more strongly with the null hypothesis than the value actually observed, right? So that is a basic definition of the p-value, right? It's basically saying if the null hypothesis is true, what is the probability of observing this specific sample mean? The p-value is an area under the student's t-curve with n minus 1 degrees of freedom. And this area will either be in the left tail, the right tail, or both tails, depending on the type of test, right? So this is really no different from what we learned in the previous section, except that the areas, or the tails being described here, correspond to that of a student's t distribution curve, not a normal curve. So let's go over the table and look at what the table can tell us about p-values. Okay? Now, when using a table, most of the time we will not be able to find the p-value exactly. Instead, we can only specify that the p-value falls in between two other values, which we can obtain from the table. So let's take a look at how that works. In the example we just looked at, the sample size was 76, which means the degrees of freedom was 75. So if you go over to the student's t table, which we've used already in the section on confidence intervals, it's table A3 in the appendix of your textbook. And the column on the left is labeled degrees of freedom. So in that column, you want to find your desired degrees of freedom, which would be 75. Well, in this case, 75 does not appear on the table because it jumps from 60 to 80. So the rule of thumb in that case is that you should always choose the number that's closest but smaller, right? The closest number that's smaller is 60. So we'll choose the row corresponding to 60 degrees of freedom. Now, in order to find the exact p-value, you would have to find the exact number 3.144 somewhere in this row, which most of the time you won't. So instead, what you do is you find the two numbers that are closest but fall on either side, the two numbers that bracket the observed test statistic, right? In this case, we see that the two numbers in this row that bracket 3.144 are 2.915 and 3.232. Now, for both of these numbers, we would like to go up to the top of the chart, and there's this row that we haven't used yet called area in right tail, right? These values here are the areas to the right of the numbers given in the chart, right? So in other words, we could say that if our test statistic was exactly 2.915, the p-value would be 0.0025. If my test statistic was exactly 3.232, the p-value would be 0.001, right? In reality, my exact test statistic is 3.144, right, which falls somewhere in between these two numbers, which means my exact p-value will fall somewhere in between these two numbers, right? So from the chart, we can conclude that my p-value is a number somewhere between 0.001 and 0.00225. Now, every number within that entire range of values is smaller than 0.05, right? So even though the chart does not allow us to determine the exact p-value, it does allow us to narrow it down to the point that we can still conclude the test, right? Because we can still conclude that the p-value is smaller than 0.05, right? So we can conclude that the p-value is small enough to reject the null hypothesis at the 0.05 level of significance. So that is how the chart works for at least narrowing down the possibilities for what the p-value is. Here's a diagram that kind of illustrates that, right? In the row corresponding to 60 degrees of freedom, our observed test statistic, which was 3.144, fell in between the values 2.915 and 3.232, right? The area to the right of this value was 0.0025. The area to the right of this value was 0.001, which means the area to the right of our observed test statistic will fall somewhere between 0.001 and 0.0025. Notice that the student's t-distribution chart only gives areas to the right tail. All the numbers in the chart here are positive numbers, and the areas at the top are areas in the right tail. However, you can also use this for left tail tests because of the symmetry of the curve, right? The area to the left of a negative number is the same as the area to the right of a positive number, right? So if your computed test statistic in your problem that you're working out ends up being a negative number, the best thing to do is just to drop the negative sign, turn it into a positive, and then proceed exactly the same way, right? Find degrees of freedom, the two numbers that fall on either side of the positive version of your test statistic, right? And then look up the corresponding areas in the right tail. And then, of course, if you have a two-tailed test, then the step you would want to take is take each of the numbers, the area in right tail numbers at the top of the chart, and multiply them by 2, right? Because the p-value for a two-tailed test has to account for both the right tail and the left tail, but those areas will both be the same size because of the symmetry of the curve, so we just double the areas to account for that, okay? Right, so it makes that statement right here, right? The area in both tails is between 2 times 0.001 or 0.002 and 2 times 0.0025 or 0.005. Okay. Let's look at another example. Generic drugs are lower cost substitutes for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The U.S. Food and Drug Administration is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amounts in micrograms are given here, right? 2.6, 3.2, 2.1, 3.0, 3.1, 2.9, 3.7, right? So there are 7 numbers there corresponding to the 7 subjects who participated in this test. The question is, how strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? Use the 0.01 level of significance. Notice because the word there is differs, that tells us that we will be setting this up as a two-tailed test when we establish our hypotheses. But before we establish the hypotheses, it's a good idea to check our assumptions. The sample is a simple random sample, but it's a small sample, a sample size of 7, right? So if the sample size is less than 30, then we want to feel relatively confident that it comes from a population that is approximately normal. And an easy way to check this is to create a dot plot of the data, a number line, and we place a dot corresponding to each of the 7 data values. And what you observe in the dot plot here is that it looks pretty uniform, right? The dots are pretty evenly spread out. There's no evidence of strong skewness or outliers. So that's good enough evidence to satisfy that assumption, so we can proceed. So then we can establish our hypotheses. The null hypothesis is the assumption that the ointment is working as it's supposed to, which means the mean amount is 3.5. And then because the word used was differs, we'll set up the alternate hypothesis as a two-tailed test using the not equal to symbol, not equal to 3.5. And then in the problem, the only data that's given is the raw data, the 7 numbers, right? So in order to compute the test statistic t, we have to have a sample mean and a sample standard deviation. Both of those numbers can be computed from the sample data. And if we do that, the sample mean, which we obtain by adding up the 7 numbers and dividing by 7, that gives us 2.9429. The sample standard deviation is computed using the sample standard deviation formula, which we covered back in chapter 3 of the class. Of course, you can also use technology to find that number, but if you compute it, you get 0.4995. The next step is to find the test statistic using the t-value formula. And again, we make the assumption at this point that the null hypothesis is true. So we'll plug in 3.5 for the population mean. And then when we divide by s over the square root of n, we get 0.1888. So the t-value ends up being negative 2.951. Because the sample size is 7, the number of degrees of freedom is 6. This is a two-tailed test, so the p-value is the sum of the area to the left of the observed test statistic, which is negative 2.951, and the area to the right of positive 2.951. Okay? If we use the table, again, we would find the row corresponding to 6 degrees of freedom, and then we would find the 2 numbers in that row that bracket 2.951. Okay? if you go to the table and look at the row corresponding to 6 degrees of freedom, you will find the two values closest to 2.951 are 2.447 and 3.143. And then you would go to the top of the chart and look up the area in right tail corresponding to both of these numbers. The area to the right of 2.447 is 0.025. The area to the right of 3.143 is 0.01. So the area in the right tail, or the area to the right of 2.951 is a value between 0.01 and 0.025. Now, because it's a two-tailed test, the p-value will be twice the area in the right tail. So we would double both of these values, right? And we would conclude that our p-value falls somewhere between 0.02 and 0.05. Okay? And then we will compare that to our given value of alpha. We were asked to conduct the test at the 0.01 level of significance. Now, if the p-value is between 0.02 and 0.05, it's a pretty small p-value, but it's still larger than 0.01, right? So at the 0.01 level of significance, we will not reject the null hypothesis. And we will say there is not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean might be equal to 3.5 micrograms. Okay, so let's now go over how to do this type of hypothesis test using the TI-84. So we'll revisit the same two examples, starting with this weight loss example, right? This is kind of a rehash, right? It's of what we've already covered. Assumptions, we've already covered that. Set up your hypotheses, right? Test statistic. This is all review. What I want to do is get ahead here to where the function on your calculator, here we go, right? So you'll go to the tests menu, press the stat button, and then highlight the tests menu. In the previous section, the option we chose was the first one, z-test. But this time we will be using t-test, the second one in the list there. Okay? And if you select the option, again, for input, there are two options for input, either data or stats. For the weight loss example, we would use stats because the sample mean and the sample standard deviation are both given in that example. And you would just type those values in. For the second example, the one about the ointment cream, we would use data as the input because in that one, all that's given is the raw data. So we'll go over both examples here, starting with the first example. Right, so here's our example. Can you conclude that the mean weight loss is greater than 0? So highlight the test menu, select t-test, make sure that stats is selected as your input option. For mu sub 0, type in 0 because that's the value corresponding to the null hypothesis, right, which is that mu equals 0. Oopsie, sorry. X bar is the sample mean. That is given as 2.2, right? SX is the sample standard deviation. That is given as 6.1. Type that in. N is the sample size, which is given as 76. And then here you can choose two-tailed, left-tailed, or right-tailed. We would select this option because that's for right-tailed. Then highlight the word calculate and press enter. And it gives you a readout of several values, but the most important one is the one labeled P. That is your p-value, right? Which comes out to be about 0.00119. So for this method of conducting a hypothesis test, the calculator does have a very distinct advantage over the table because the calculator allows you to get an exact p-value, whereas the table only allows you to narrow it down to within a range of values, right? So once we have the p-value from the calculator, we can just directly compare it to our value of alpha. And since 0.0012 is smaller than alpha, we reject the null hypothesis and we conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. Now, let's go over the next example, right? The one regarding the antifungal ointment. Here's the problem description again. And you see the only data that's given are the seven sample data values right here. Okay? And we're testing at the 0.01 level of significance. Always good to check your assumptions, which we've covered that already, right? Look at the dot plot. Establish your hypotheses, right? And this time, if we are using the calculator, the first thing we need to do is enter your data into the list editor, right? Which again, to do that, you press the stat button and then make sure the word edit is highlighted and press enter. And then you just type your 7 numbers into L1. After the numbers have been entered into L1, you press the stat button again, highlight the word tests, and then choose t-test. And then for input, make sure that data is selected. From U0, that's the null hypothesis, so you should type in 3.5 for that. Under list, it should be L1, right? It should refer back to L1 because that's where we typed our data in. Frequency should just be, it defaults to 1. You can just leave that alone. We want a two-tailed test, so we select the option for two-tailed, do calculate, and here's your results down here, right? Gives you your t-value, your p-value, your sample mean, sample standard deviation. Of course, the number that's the most useful here is the p-value, 0.02558, right? And then we can compare that to our value of alpha. It's larger than 0.01, so we do not reject the null hypothesis at the 0.01 level. And we say there is not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean may be equal to 3.5 micrograms. So that wraps up this section. We've looked at the assumptions for hypothesis tests for testing about a mean when sigma is unknown. We've looked at how to perform the test using the p-value method and how to find the exact p-value using your calculator, and also how to estimate a p-value from a table. In the next section, we will go over the process for conducting a hypothesis test about a proportion. So that wraps it up for this one, so thank you.